Hey guys, and welcome to our second video on dimensional analysis. So if you recall, in our first video, we introduced the concept of dimensional analysis as the procedure by which the units in terms of which a measurement is expressed are changed. So after defining dimensional analysis, we proceeded to perform a couple of examples utilizing the fundamental units of length and mass. So that is to say, the meter and kilogram respectively. So in today's video, we're going to perform a couple more examples of dimensional analysis, utilizing not only fundamental units, but also derived units. So as we discussed in our first video, a fundamental unit was defined as a physical quantity in terms of which larger measurements are going to be reported. So these physical quantities are going to be assigned variables or notation for the purposes of identification. So say we wanted to obtain the length of an object utilizing the metric system. So the fundamental unit of length in the metric system is the meter. Let's keep that in mind. So say this line that I'm drawing corresponds to the length enclosed by 1 meter. Thus, we would report the length of an object as a multiple of that fundamental unit. So I'm going to say 2 meters. Now, on top of this significance, fundamental units cannot be expressed in terms of simpler notation. Let's visualize a fundamental unit as a variable. It's independent. It can't be expressed in terms of anything simpler than itself. And a meter happens to be the fundamental unit of length in the metric system. Now, with regards to the metric system, there are actually 7 fundamental units, each one corresponding to a different physical property. We just discussed meters, which are basically used to measure length. Kelvin are the fundamental units used to measure temperature. The candelas are the fundamental units in terms of which luminosity is expressed. The kilogram is the fundamental unit for mass. Amperes are the fundamental unit for electrical current. Seconds are the fundamental unit for time. And moles are the fundamental unit for quantity. So collectively, these are the only 7 fundamental units in the entire metric system. But by combining them through arithmetic, you can actually get another class of units known as derived units. So, like I just said, derived units are basically the end result of multiplying, dividing different fundamental units, and derived units account for the bulk of units in the metric system. One of the most well-known derived units in the metric system is the Newton. So we know that a Newton is basically a unit used to quantify force, and as a derived unit it can be broken down into the fundamental units that comprise it. So force is basically the product of the mass of an object and the acceleration due to gravity on that object. We can further simplify the acceleration term into an expression containing length and time. So this expression corresponds to the most fundamental terms in which the force can be expressed. As you all know, the unit for mass in the metric system is a kilogram, the unit for length is a meter, unit for time is a second. So we could rewrite this expression as kilogram meters per second squared. So another physical property expressed in terms of derived units is pressure. And pressure is defined as the ratio of an applied force to the area across which that force is distributed. So we just described force as being a function of mass, length, and the square of time. Area is equal to length squared. So we can rewrite our expression F over A as m times L or mass times length, divided by the square of time multiplied by length squared. So remember that our length squared term corresponds to the area, and then the remainder of our expression, mass times length over time squared, corresponds to the applied force. So canceling out the additional L variable would give us mass divided by the square of time times length. And then if we were to substitute these physical properties with their corresponding fundamental units in the metric system, remember the fundamental unit of mass is the kilogram, fundamental unit of time is the second, so second squared, and then the fundamental unit of length would be the meter. And this particular selection of fundamental units would give us the derived unit of pascals. And again, a pascal is the unit for measuring pressure in the metric system. So now that we've discussed the difference between fundamental and derived units, we can discuss one more concept before finally jumping into our unit conversion calculations. And that would be the concept of unit prefixes. Unit prefixes allow us to reduce the number of figures that we need to express large and small quantities, and they thus allow us to study and interact with exceedingly large and exceedingly small magnitudes. Now, the concept of the unit prefix allows us to do this by multiplying your base unit by some factor of 10. So these are some examples of unit prefixes utilized in the metric system. And so going from start to finish, the prefix femto corresponds to a factor of 10 to the negative 15th. Pico corresponds to a factor of 10 to the negative 12th. Nano corresponds to 10 to the negative 9th. Micro corresponds to 10 to the negative 6th. Milli corresponds to 10 to the negative 3rd. Deci corresponds to 10 to the negative 1st. Kilo corresponds to 10 to the 3rd. Mega corresponds to 10 to the 6th. And giga corresponds to 10 to the 9th. So not mentioned here is the unit prefix centa, which corresponds to 10 to the second, or negative second. I guess I'll add that right here. So let's look, for example, at a fundamental unit of length, the meter. So a meter would be multiplied by a factor of 10 to the 0th, which is 1. 1 meter is 1 meter. But what about a kilometer? Well, we know that the prefix kilo corresponds to 1 times 10 to the 3rd. So a kilometer is going to be equal to 1 times 10 to the 3rd meters. 1 kilometer is going to be equal to 1 times 10 to the 3rd meters. Well, how about a millimeter? A milli prefix corresponds to a factor of 10 to the negative 3rd. So a millimeter is equal to 1 times 10 to the negative 3rd meters. I could do another example. A nanometer would be equal to 1 times 10 to the negative 9th meters. So let's say that we were given a magnitude of 1 meter and we were asked to express it in terms of kilometers. Well, we already said that there are 1,000 meters in a single kilometer based on this term over here. That would become our conversion factor. So 1 meter multiplied by 1 kilometer over 1,000 meters would give us our length in kilometers, right? So our unit meter would cancel out, and we would be left with 0.001 kilometers. Similarly, say that we were given 1 meter and we were asked to express its equivalent length in millimeters. Well, we know that there are 1 times 10 to the negative third meters in 1 millimeter. And so we could convert that into a conversion factor. We'd be multiplying 1 meter by 1 millimeter divided by 0.001 meters. And that would give us a solution of 1,000 millimeters. So after going through all that math, you're probably wondering whether there is an easier way to perform unit conversions from one unit prefix to another. And there is. You may recall that when we converted from meters to kilometers, we multiplied our original unit, the meter, by a conversion factor. 1 kilometer per 1,000 meters. This was basically the equivalent of dividing our original term by 1,000. So rather than going through this procedure, what we can do instead is simply recognize that we are moving the decimal in our original term by a certain number of spaces. So to go from to convert 1 meter into its equivalent length in kilometers, we're basically moving our decimal to the left by 3 spots. That's a relatively easy way to look at it. So I've basically converted 1 meter into its equivalent length in kilometers. But say now that we wanted to convert from kilometers to decimeters. So a decimeter basically is multiplied by a factor of 1 times 10 to the negative first. Kilometer, 1 times 10 to the third. The difference between these two units is going to be 1 times 10 to the fourth. So if we're going from kilometers to decimeters, we're essentially moving our decimal point 4 spaces to the right. So what is that going to give us? (10 decimeters). Now let's do another example. Say we want to convert from decimeters to millimeters. Well, if you look at the scale above, you'll see that the difference between the milli and deci prefix is a factor of 10 to the second. So if we want to convert from 10 decimeters to the equivalent length in millimeters, what we have to do is move the decimal point 2 units to the right. So what would that give us? Well, 1,000 millimeters. And then I guess we'll do one more example. Let's say that we wanted to convert from 1,000 millimeters back to the equivalent length in kilometers. Well, the difference between the millimeter prefix and kilometer prefix is a factor of 1 times 10 to the sixth. So we're basically going to be moving our decimal place to the left by 6 units in order to give us our equivalent length in kilometers. So 1,000 millimeters is going to be equal to 0.001 kilometers. So I guess the last thing we should go over is how you know whether to move the decimal place to the left or to the right during any particular unit conversion. So everything actually boils down to your conversion factor. So let me erase all of this and go back to our original method for achieving these unit conversions. So say we're given 1,000 millimeters. Well, if we want to convert that to kilometers, we're multiplying that by our conversion factor, where 1 kilometer is equal to 1 times 10 to the 6th millimeters. Now, if the ratio of your numerator to your denominator happens to be less than 1, then you're moving your decimal place to the left. So let's say that we were given 1,000 kilometers and we were asked to convert to meters. Well, in this case, our conversion factor would be 1 meter is equal to 0.001 kilometers. And the ratio of our numerator to our denominator is now greater than 1. So whenever your conversion factor is greater than 1, then your decimal is moving to the right. So 1,000 kilometers is going to be 1 times 10 to the 6th meters. So in summary, if you're given a measurement in terms of 1 unit, x, you're going to have to multiply it by some conversion factor, y over x, to get your measurement in terms of the finalized unit, y. And if your conversion factor, y over x, is larger than 1, then y is going to be larger than x. If your conversion factor, y over x, is less than 1, then y is going to be less than x. So now that we've covered this topic, we can move on to our unit conversion examples. And all of these unit conversions deal with measurements of pressure. The first example asks us to express 108 kilopascals in terms of torr. So I've already gone ahead and gotten the conversion factor for this. 760 torr is equal to 101.325 kilopascals. So, if we wanted to convert from 108 kilopascals to its equivalent magnitude in torr, we would multiply 108 kilopascals by its associated conversion factor. Now, what would the ratio be in said conversion factor? So, the unit that we're trying to convert away from should be in our denominator. that is to say 101.325 kPa. And in our numerator should be the unit that we're trying to convert to, so 760 torr. So our units of pressure in kilopascals cancel out, and what we're left with is our solution, which turns out to be 810.067 torr. Our next practice problem is a little bit more convoluted because we're given two conversion factors. So this question asks us to convert from 0.975 bar into its equivalent magnitude in atmospheres. And we are given two relationships to help us solve this problem. First of all, we're told that 1 bar is equal to 1 times 10 to the second kilopascals. And then we're also told that 1 ATM is equal to 101.325 kilopascals. So how would we go about converting from bar to atmospheres? So to solve this problem, we're going to need two separate conversion factors. First, we'll be multiplying our pressure in bar by the ratio of bar to kPa. So this basically corresponds to our first conversion factor. So 0.975 bar multiplied by 1 times 10 to the second kPa over 1 bar. So the purpose of this unit conversion, or this conversion factor, is to eliminate the bar term from our equation. Then we would multiply our expression by the second conversion factor, in which 1 ATM is defined as being equal to 101.325 kPa. So 1 ATM over 101.325 kPa. So this second conversion factor would eliminate units of kilopascals such that our last remaining unit would be ATM. And this expression, once solved, will give us our solution. So you're basically multiplying 0.975 bar by 1 times 10 to the second, so by 100, and then dividing that number by 101.325 to give you a solution of 0.962 ATM. So there's nothing special about our third example problem, where we're asked to convert from 22.5 kilopascals to its equivalent value in atmospheres. We already know from the second example problem that for every atmosphere, every ATM, you have 101.325 kilopascals. So what we're going to do here is multiply our initial pressure, 22.5 kilopascals, by the ratio of ATM to kPa. So again, for every unit of ATM, have 101.325 kilopascals. And as you've already seen, units of kilopascals in the numerator are going to cancel out with the units of kilopascals in your initial measurement to give you your solution in atmospheres, which is 0.222. Last but not least, we're asked to express 770 torr in terms of pascals. And you're also given two different conversion factors to solve this problem. The first states that 760 torr is equal to 101.325 kPa, and the second conversion factor states that 1000 kPa, or rather 1000 pascals, is equal to 1 kPa. So the second conversion factor is actually something that we discussed earlier in our video when we were talking about unit prefixes. In either case, in order to solve this particular problem, you're first going to multiply 770 torr by 101.325 kilopascals per 760 torr. This first conversion factor basically cancels out units of torr from your expression. And then last but not least, you multiply your term by 1000 pascals per 1 kilopascal, which eliminates your units of kilopascal, and you're left with a solution of 1.027 times 10 to the 5th pascals.